Hello everyone, I am Sahishnu Manohar from CSCB. Here I am presenting my tech talk on chemistry. The topic assigned to me is adsorption mechanisms of heavy metal ions from drinking water by weakly basic anion exchange resins. Here we move on to the contents of the presentation. We start off with abstract, introduction, principle, material method, result, conclusion, and references. So here we go on with abstract. So heavy metal microcontaminants can be removed from water sources such as rivers and lakes using variations of conventional treatment technologies. Weakly basic anion exchange resins offer the best ability to remove trace amounts of heavy metals of high selectivity. This slide discusses how weakly basic resins absorb heavy metals using two different approaches. The removal of mercury, cadmium, and lead ions is based on the fundamental theory of coordination chemistry. The mechanism is not ion exchange but attractive adsorption of heavy metal salts. However, the marked preferential adsorption of chromate by weakly basic anion exchange can be explained using the traditional theory of ion exchange. A lab scale study produced positive results for the removal of trace amounts of heavy metal ions from drinking water. So we are moving on with introduction. Wastewater of mineral processing industries normally contains a variety of hazardous heavy metals and sometimes may be discharged without adequate treatment. The polluted drinking water source contains heavy metal contaminants normally with a concentration up to 100 to the power G, where for mercury is like 1 to 10 divided by G. The normal cation exchange cannot exclusively remove heavy metals due to exchange competition with alkaline and alkaline earth metal ions. Principle. A possible way to eliminate trace amounts of heavy metals is by introducing weakly basic anion exchange resins. The functional group of these resins are chiefly primary, secondary, and tertiary amino groups. Using a primary amino group as an example, the equilibrium does exist at neutral pH. The reaction goes as RNH2 plus H2O gives rise to RNH2 H2O. The principle used are principle of extractive adsorption. Using a primary amino group as an example, the equilibrium does exist at neutral pH. The reaction goes as RNH2 plus H2O gives rise to RNH2H2O. In addition, because this process is not an exchange of ions, using mercury chloride as an example, the process can be written as RNH2 plus Hg2 plus 2Cl gives rise to RNH2 plus Hd2 plus 2Cl. As the stability of Me and N bond is lower than that of NH bond, consequently, regeneration of resin can be achieved by applying a strong acid, RNH2 plus Hg2 plus 2Cl, with an acid which is H2SO4, nothing other sulfuric acid, gives rise to RNHT plus HSO4 plus HgCl2. The resin cannot be reused directly for absorption of heavy metal salts. Reaction RNH3 plus HSO4 plus 2NaOH, here we're using a base, gives rise to RNH2 plus Na2SO4 plus 2H2O. Principle of ion exchange. In natural water and at a neutral pH, chromium usually occurs at CrO2 and HCrO, which cannot be eliminated in the same way as explained above. In the use of weakly basic anion exchange resins has been tested for the removal of chromium for neutral pH condition. Assume that the elimination of HCrO species by introducing resin in the hydrate form can be written as RNH2 plus H2O plus HCrO4 gives rise to RNH3 plus HCrO4 plus HOH. This process is not the extractive removal of heavy metals, but the removal of ion exchange. For regeneration, the exchanger can be converted to hydrate form by means of caustic alkali or lime. RNH3 plus HCrO4 plus NaOH gives rise to RNH2 plus H2O plus Na plus HCrO4. Material and methods. Weakly basic anion exchange resins. Before the experiments, the resins should be pre-treated with hydrochloric acid of concentration 0.5 mole and sodium hydroxide with concentration of 1 mole to remove impurities. After rinsing by means of demineralized water, the resins can be applied for treatment of drinking water. In the experiments, 4 kinds of commercially weakly basic anion exchange resins were applied for the removal of heavy metals from drinking water. Test and installations. The experiments were carried out in laboratory scale installations as shown. The resin material was packed in filter column with an inner diameter of 2.8 centimeter and length of 28 centimeter. Raw water was first pumped to an intermediate buffer vessel and it flowed through and filter in the downstream direction. Samples were automatically taken from the effluent. The pH was measured and recorded automatically. The effluent sampler flow rate amounted to 20 BV. BV is the bed volume based on empty filter volume. Adsorption equilibrium. The equilibrium experiments were carried out for static conditions. Samples of resin material 0.5 to 10 gram were soaked in with 200 ml CDNOS2 bearing original solution. After equilibrium was established, the solution was analyzed for heavy metal concentration. The equivalent fraction of heavy metal in the resin phase was determined by difference between initial and equilibrium concentrations. Analytical. Heavy metal concentrations were determined by means of flame atomic adsorption spectroscopy using a variant spectra 300 instrument, which has a detection limits of 0.001 mg per liter to 1 CAD CD, 0.01 mg L1 for PB, which is lead, and 0.0001 mg per liter for Hg. Effluent pH values were monitored using standard Scott electrodes and a Nick digital pH meter 646. Concentrations of organic matter expressed as TOC were measured by Shimadzu TOC 500 analyzer. Results. Extractive removal of heavy metals based on the theory of coordination chemistry. Trace amounts of heavy metal ions were removed with high efficiency. However, concentration of other background components varied a little after the treatment. The same results were observed for resin material. Duolite A7, which suggests the weakly basic anion exchange resin, exhibited high selectivity for trace amounts of heavy metals without significant change of the water composition. Removal of chromium based on theory of ion exchange. With the increase of SO4, sulfur oxide in the original solution, the rapid decrease of equivalent of chromium in exchanger phase can be observed. Furthermore, breakthrough curves of chromate were obtained using the small column with an inner diameter reveal the greater difference with the non-buffered demineralized water as raw water. The adsorption of chromium is affected by the increased sulfate concentration. This is very different from the case of the removal of cadmium in the raw water in presence of chloride. Regeneration. Regeneration is a very important process in ion exchange method. Different adsorption approaches, extractive adsorption or adsorption by ion exchange, lead to different regeneration processes. With respect to regeneration of chromium loaded exchanger, however, the bulk part of chromium was eluted by the treatment with NaOH. That means the chromium was removed with the treatment of NaOH, and the treatment with sulfuric acid was not necessary. The whole regeneration process can be completed by the consumption of 4 BV bed volume of 4% NaOH. The amount of chromium is approximately equal to the amount of adsorbed in the service cycle. Conclusions. We are coming to the end of the presentation. The application of commercially available weakly basic anion exchange resins allows extremely selective elimination of trace amounts of a variety of hazardous cationic heavy metals and the elimination of chromate anions from raw drinking water supplies. Trace amounts of mercury, cadmium, and lead were removed by weakly basic anion exchange resins with the formation of coordinate covalent bond. This process was kind of extractive adsorption of heavy metals. Different adsorption approaches lead to different regeneration processes. Hg loaded resins need 4 bed volume of sulfuric acid solution, which varies from 0.5 molar per liter. For complete recombination and the same amount of NaOH, we need 1 mole per liter. For neutralization, however, the resin loaded with Cr, only NaOH can lead to almost complete regeneration. References by Benes P. Havlicki Speciation of mercury in natural waters, top environ health in 1979. The page numbers are 175 to 202. Lockwood, R.A., Chen, K.Y., adsorption of mercury by hydrous manganese oxides. Environment, say, TEC, in the year 1973. The pages vary from 1028 to 1034. Zhu Hanbin, SIG L cadmium speciation and complexation by natural organic ligands in fresh water. Analytica Chimica Act, 1988. Thank you. We have come to the end of the presentation. Thank you for sparing the time with me. This is Aishnu Manohar from CSCB, presenting you the tech talk for chemistry subject. Thank you.